for laboratory of
non-linear mechanics, yes, thank you. Bravo. Chinese Academy of Sciences in Beijing, China. Just to say that Professor Hong is editor-in-chief of the journal, which is probably the best in our field, Fatigue and Fracture of Engineering Materials and Structures. And what else can I say in that case? So, Professor Hong's specialty is very high cycle fatigue. That is a relatively new topic for us, so we will have very good introduction and then some very illustrative examples, and finally, of course, some results of research performed in this fantastic place which I visited last September. Please, Professor Hong.
Thank you, Professor Schematic. And I'm really honored to be invited to give a talk here today. And just now, Professor Schematic gave a brief introduction about me and about my affiliation. And in fact, LNM means State Key Laboratory for Nonlinear Mechanics. State Key Laboratory meaning is some kind of national laboratory in China. But anyway, I'm from the Institute of Mechanics. It's an institution under the Chinese Academy of Sciences. And I am also here a little bit praised because today so many distinguished professors here to join this seminar, to join this to join my talk, including some very special audience from the conference. So it is really a kind of international seminar, not just internal. It's an international.
4 continents.
Yeah.
We have 4 continents.
4 continents.
Only Australia.
Yeah. And very representative. I mean, so there are some very well-known figures from different continents. Okay, this is the outline of my talk today. First, I have to give a brief introduction about VeryHighCycle Fatigue. Perhaps some of them familiar with this topic, and some of them do not. So I will give you some brief introduction, and then I will emphasize 3 aspects of VeryHighCycle Fatigue. And finally, I give some conclusions, including knowns and challenges. Okay, first I will say something about VeryHighCycle Fatigue. Very simple or very quickly that VeryHighCycle Fatigue is a fatigue failure beyond 10 to 7 cycles of loading. Normally or conventionally, fatigue limit is regarded as a fatigue stress or fatigue strength at the loading cycles of 10 million. And people regard it as for this type of fatigue, this type of fatigue strength is fatigue limit. But in recent decades, people found that fatigue failure may even happen beyond this range after 10 to 7 cycles of loading, after 10 million cycles of loading. So, it's an example showing this phenomenon. This 10 to 7 cycles of loading and this conventional fatigue behavior. But after these points, beyond 10% cycles of loading, fatigue failure may still happen. So we call this very high cycle fatigue. Is different from conventional fatigue definition. And this is an example showing what is the major importance of very high cycle fatigue. It is that fatigue crack initiation is almost from the inside, from the interior of the material, the specimen. And this example showing this type of phenomenon is a poor cross-section of specimen, and is the point of initiation and the enlargement showing this type of morphology, and even the enlargement to show the detailed feature of this initiation spot. And I will go in detail about this feature, this phenomenon. And we always say very high cycle fatigue is a very important topic or very important area to be investigated, because many engineering structures require a large number of cycles of, say, performance, always beyond 100 millions of cycles. And we may have an idea that such type of very high cycle is very easy to be reached. For example, if the frequency is 1 Hertz and just a little bit more than 3 years, it will reach 100 million of cycles. And if the frequency is 10 Hertz, just for 1 year, it will be more than 300 million cycles. Like airplanes, high-speed trains, special voyages. So this is important in terms of engineering applications, and also very high cycle fatigue behavior and mechanism is different from the case, from the situation of high cycle and low cycle fatigue. So new mechanisms to be revealed, and also new design regulations to be established. So we say very high cycle fatigue is very important. And here I will give you two very interesting or very sad examples. One was happened about 4 months ago in the US. It's Southwest Airlines flight 1380. And I think perhaps most of us know this case. There's a Boeing airplane, and there's a damage of engine blade, made of titanium alloy, and the damage of blade caused the damage of the cowling and to hit a window. This accident killed a passenger. It was a lady. And then later examination showed there's a phenomenon of fatigue crack initiation and also propagation. It's due to mental fatigue. And what I would like to emphasize is this airplane is already 18 years old, meaning it has been experienced is more than 9 billion cycles of loading if we consider the rotation of the turbine. If we just consider the vibration of the airplane, it experienced about 200 millions of loading cycles. So it's experience a process or a kind of very high cycle fatigue process. So this is very important point. So sometimes I said, for some new structures, new vehicles, they're very safe, no problem. But for some old ones, we should be very careful. And I will say something in detail in my later slides. Another case I think all of us know is the Asian tragedy of high-speed train. It happened about 20 years ago, and perhaps all of us know these very well noticed pictures. Of course, all of this I found from the internet, but it's very sad case to kill 101 people and also another 100 injured. But what I like to notice, what I like to emphasize is that this high-speed train has been serviced for more than 7 years at the time of the tragedy, of the delay. And it's a fracture of the wheel. It's a kind of called wheel type, and the final layer of the wheel fracture due to fatigue. And it's a kind of very sad story to cause a series of damage and cause this type of tragedy. And I just like to emphasize that this high-speed train has 7 years of service and has experienced more than 1 billion cycles of loading. Again, for the new ones, they are safe. But for some old ones, we should be very careful. Sometimes I also say this or say this concept in some conference, discuss with some people, even also in China. Now high-speed trains are quite popular, and people are all very happy because, and also they are quite new. I said, perhaps after 10 years, we should be very careful because perhaps there could be some very, very tiny defects developed. So we should have some very strict regulation for this. And then I would like to mention the origination of very high cycle fatigue research. I said conventional fatigue is the fatigue behavior less than 10% cycles of loading, but very high cycle fatigue is beyond 10% cycles of loading. And the origination of very high cycle fatigue is in about 35 years ago. This is an example for high stress sphere to show fatigue failure may happen after 10% cycles of loading. And this example showing crack initiation from the interior of the specimen. And also for titanium alloy, I noticed is almost the first paper for titanium alloy of very high cycle fatigue. And these 10% cycles. The previous one for high stress sphere it was done by Japanese researchers, and this one was by Swedish researchers. Of course, Professor Rich also did some very early work in, I think it's in late 80s or early 90s, I think. Right? There was a special issue of feminist, and Professor Rich was one of the authors of a paper in that special issue. And I mentioned before, in the early 80s, by Michael and his co-authors and Ashwin and his co-author, they first time reported the behavior, the phenomenon of VeryHighCycle fatigue. But they just said they just called long-life fatigue. But in '86, Stenzer and his co-authors, they call this VeryHighCycle fatigue, the first time in a research paper. So I like to say that the contributions by Japanese researchers, Swedish researchers, and also from Austria, after their contribution, or based on their contributions, is the origination of VeryHighCycle fatigue research. So it is almost the early days, the research of early days of VeryHighCycle fatigue. And this topic or this regime has been quite noticed by the fatigue community. And since the year of '98, there was an international conference on VeryHighCycle fatigue. And then almost every 3 years there's a conference number 1 to number 7. And the next one we had in 2 years in Japan. And this is the one last year in Dresden, Germany, and also I had been invited to give a talk there. I use this slide. The reason for this is that I gave a talk some months ago in France, this International Congress on Fatigue, and the professor from Germany, what's the name? It's a very famous professor. No, he gave a contribution on interaction between crack and dislocations. Sorry? What's the name? No, Sosila. No. He's a guest editor of a special issue to commemorate Professor Patias. Sorry to ask, but sometimes my heart is some problem, and I will recover in the later class. Anyway, because he raised a question that when someone talking VeryHighCycle fatigue, we should mention this series of international conference, and then later I put this the first one was organized by Professor Patias from France. Anyway, so perhaps I used too much time for the introduction, and I will emphasize 3 aspects of VeryHighCycle fatigue. So the first aspect is the essential characteristics of VeryHighCycle fatigue, and in this part I emphasize 3 points. The first one is internal crash initiation. Second is SN curve style, and the third a scrap initiation line. Three points. So I would emphasize in this part. And this is an example of very high cycle fatigue. We may see that initiation spots, and there's a morphology called fisheye, and around the initiation spot there's a rough fracture surface called fine granular area. And this is the schematic to show this morphology. Initiation spot, FGA fine granular area, and fisheye, and then crack growth region. And this is the case for very high cycle fatigue. For high stress field. And this is an example showing the initiation spots, the FGA region, and fisheye. And we may notice that this example is due to the loading of low-tolerant bending. So the initiation spot is somehow close to the specimen surface. And the previous one is subject to axial loading. So the initiation location is somehow away from the surface. So it's different. One of the reasons is due to the different styles or different modes of loading. And we measure the size of this area of FGA, fine granular area, to show the size is between 40 and 100 microns, very small size. I measure this. This is initiation area. Also, we have more data to show this, and also we use the parameter of delta K, is the stress intensity factor range, to characterize this small area. And the data show the delta K FGA is between 4 and 6 megapascal volume here. And we collect a large number of data from the literature to show the size of FGA as a function of maximum stress. And we see that most of data within the low bound of 4 megapascal volume and the upper bound of 6 megapascal volume. So we said this value of delta K for this initiation region is very stable. For different loading examples, different loading cases, and different size of initiation region. No matter how these type of changes, the delta K value is very stable. So it's very interesting. And then we said that the size of FGA is an intrinsic characteristic region, or intrinsic characteristic size for interior propagation. So this is our consideration, is our we try to propose the concept for very high cycle fatigue behavior. And previous ones are the cases of high stress steel. And then here are examples for titanium alloys. And also you may see the initiation region of fisheye, and also in the initiation size, a kind of rough area. But the difference is for titanium alloys, the initiation size is due to the coalescence of cleavage facets always from alpha phase of titanium alloy. So it's schematic for this coalescence of facets and rough area and then fisheye and crack steady growth or stable growth and finally failure. Again, these are the examples. There are examples from titanium alloys initiation spot. And this picture shows the small piece of fracture flexes from alpha phase. This another one. Is straight ratio of -1, straight ratio -5. Apart, sorry, 4.1 and 0.5. And for titanium alloys, we also measure the size of FGA of the eye region, and it's between about 120 and 390 microns. It's still quite within a certain range. And the value of theta K is between 6 and about 8.7 megapascal per liter. That is also similar to the case of high-speed. It's quite stable. So this type of phenomenon is not just for high-speed, it's also for titanium alloy. So we try to estimate the threshold value, or just to find what can we estimate, how can we calculate the value of this the value of delta K for this crack initiation region. And we use these expressions. The first is the plastic size of crack tip, and the other is the size of characteristic microstructure of the material. And the important point is that we assume when the plastic size and crack tip equals to the characteristic size of the material, the development of this initiation region will be completed. But of course, you may argue this type of assumption. But we just made this type of assumption, and then we are able to get this expression to show the value of theta K FGA is just a function of shear modulus and Berger's vector of the material. So it's very simple and very clear to tell us what will be connected with this very important variable in relation or responsible for crack initiation. And we may get the result for spheres, for titanium alloy, for aluminum alloys. Such values are quite in good agreement with experiments. So this is the first characteristics I would like to mention for VeryHighCycle. And the second aspect is about SN curve, the straight and failure cycles of T-line. This is the result from Professor Sakai's group. And they did or they performed experiments, used the same type of materials and type of specimen and facilities, and then they collect all the data from 6 laboratories to cite the kind of round-robin test. And so here, they use a type of locating bending or rotary bending. So that is failure on the surface, and this group of VeryHighCycle Fatigue due to internal crack initiation. And there's a schematic showing that the fatigue failure of VeryHighCycle Fatigue, or the SN curve of VeryHighCycle, is kind of stepwise or duplex, SN curve. That's a very special, very unique feature of VeryHighCycle Fatigue. this experimental result and this schematic to show this. And it is very likely that this type of SM curve style is due to the different mechanism of crack initiation. The first part is due to crack surface initiation, and the second part is due to internal crack initiation. And this is the case for high-strength titanium alloy. The previous one is from high-strength steel, and also so different parts of the SM curve. Okay, so previous ones are the second point of characteristics, and then the third one is crack initiation line. We try to estimate these points. What is the initiation line of VeryHighCycle Fatigue? And we try to use Paris relation. And the point is that, of course, we know the total fatigue line. And now, what we'd like to get is the initiation line. So, if we know the line of n1 and n2, and we are able to get the initiation line. And n1 is from the boundary of FGF to the boundary of fisheye, and n2 is from the boundary of fisheye to the boundary of final friction. So we don't know initiation, how much contributed by initiation, but we know the total value. And if we can get these two values, these two results, these two data, and we are able to obtain the initiation line. And based on these points, this consideration, we are the same and someone and some two there, and then we can obtain, or we obtain these results for high-strength steel and also titanium alloy. And the important thing is for VeryHighCycle Fatigue, the initiation line is so large that it takes more than 95% of the total fatigue for high-strength steels and also for titanium alloys. So I just reiterate for the fatigue damage, including or containing VeryHighCycle fatigue, the majority of fatigue line is consumed by the initiation phase, initiation process. So it's a very, very important phenomenon for VeryHighCycle fatigue. So it's quite dangerous for engineering structures. And if we know the line consumed by initiation, and also we know the size of this initiation area, we can get an average crack growth rate or crack extension rate. So it's simple. And this example for high-strength steel and for titanium alloy. And we notice that the rate is so slow for high-strength steels, 10 to the minus 12 and 10 to the minus 13 in the cycle, and for titanium alloys, very, very slow. So these phenomena of this data are in connection or connected with the previous one, the fatigue line, initiation line for initiation is consumed, is almost takes a dominant part of the fatigue line. The previous ones are obtained by estimation, and recently we tried to perform direct measurements of crack initiation due to VeryHighCycle fatigue. And this is an example showing, and we should use a kind of two-step loading or variable loading. And we are, in fact, one of my students, he was lucky to catch this phenomenon, growth traces, very, very small size. And then to show the results is between 10 to minus 11 and 10 to minus 13 minutes per cycle. And we are also happy to put the data there and to see such data of our measurements can be connected with the crack growth data after initiation. So meaning our measurement for crack initiation can match with the data in the literature they measure after crack initiation. And I summarize this part. It's a quite kind of internal crack initiation for VeryHighCycle fatigue. And the value of delta K and GLI is almost constant, and it's a function of the risk factor and shear modules of the area, and more than 95% of fatigue life is consumed by crack initiation, and the crack growth rate is very, very slow. And then, very important point is we emphasize or we propose the size of FGA or this region of crack initiation is characteristic region for crack initiation for VeryHighCycle fatigue. So at this point, we may come up with two questions. First is, what is the nature of this initiation region? The second one is, what is the formation mechanism of this initiation region? So, what time is it? It's
You can
Okay.
as much time as you want.
But I have shared with you the first aspect of what I like to emphasize is the major one. Okay, and the third part, that is the second aspect I like to emphasize, the model to explain this phenomenon. And in the beginning, I mentioned some previous models available in the literature. The first one was considering that such type of crack initiation is due to the existence of hydrogen. Briefly mentioned is due to hydrogen. And the second one is due to the decohesion of carbide and matrix to induce or to cause this type of rock surface of carbonization. And the third one is due to the plastic deformation and cracking to cause the microstructure refinement and then to cause the rock surface of carbonization. And we have the others. I just would like to mention that for such previous models, they all emphasize this type of crack initiation morphology was formed before, I emphasize, before crack initiation. So this is their key point, their key concept. But such models have limitations. They could not explain different experimental observations like different materials different stress ratios, different failure cycles. So we consider it is necessary to propose some type of new models, new mechanism to explain this type of phenomenon, this type of propagation. This stage, I emphasize some very interesting examples. This one shows that for the failure cycles at 60 million cycles within very high cycle rate, there is an initiation region with FGA morphology. But for the case of 10 to 5 cycles alone, it's also it's internal clock initiation, but without rock morphology at initiation area. And this one is for different stress ratios. That's -1 stress ratio with rock surface of FGA morphology. But for 0.5 stress ratio is no, it's also internal clock initiation, but without this type of propagation morphology of rock surface. So such examples cannot be explained by previous models. So at this step, we would like to identify what is the nature of this initiation region. And for the case of high stress field, we select an example to observe the fracture surface on the top, and to see again to see the fish eye and FGA and initiation spot from occlusion, and the FGA is a rock surface, and this cross-section morphology. And it's interesting that the layer of this rock surface is about 650 nanometers. But it's just it's a kind of rough observation. And in detail, we cut a TM sample layer, use focus ion beam, and this TM image to show underneath this initiation surface, and here it is a coating to protect the surface, and it's a layer of refined microstructure, and the diffraction shows a kind of its continuous sort of meaning within the diffraction area of 200 nanometers. There are several grains inside, meaning that microstructure was very much refined. But away from this surface is an isolated diffraction spot, meaning just one grain or coarse grain. So we find microstructure there with nano-sized grains. And the further measurement to show the average size of the grains underneath surface pressure surface is about 50 nanometers. And because someone said this type of morphology just on one fracture surface, was on one side of surface, and we tried to observe both surfaces. So it's an example. Here are two fracture surfaces, but for one specimen, we may call this positive one and negative. And we can see these two can match together. It's for just the same one specimen. And we cut the film sample or TM sample at the same location and between at the boundary of crack initiation region and the fissile region. And it's not very clear, but we can see it's a continuous deflection at the initiation region for both surfaces. But away from the initiation region or just after or beyond this region is a single grade deflection. So we said the nature of FGA of this initiation region is a nanograin layer. The thickness for high stress layer is several hundred nanometers on both surfaces, and the average size is about 50 nanometers. And for titanium alloy is also very intriguing. Is also a TM sample cut by focused ion beam, and to reveal that underneath the fracture surface is a nanograin layer with this continuous diffraction pattern, and very clearly that away from the surface, fracture surface, is an isolated spot diffraction. And the size of diffraction of the detection is to 50 nanometers, so it's a nanograin layer. Then this is also an example of titanium alloy, but with different type of microstructure. It's a kind of membrane structure, and the other one is equiaxial grains, and all of them with almost the same phenomenon of nanograin layer underneath the fracture surface, and away from the fracture surface is an isolated deflection. And the thickness is 800 and 1500 nanometers. And we said for titanium alloys, and also a kind of nanograin underneath the fracture initiation region. And also we measure the average grain size at this region is about 100 nanometers. So based on such observations of crack initiation region, we propose a model of numerous separation, meaning that crack will initiate, for the case of high-stress steel, from the inclusion and, or we may say, from the interface between inclusion and the matrix. And after that, the crack surface can contact each other due to the crack closure and also the injection of residual stress. And this process may again and again, and due to a large number of cyclic. And this process is possibly to produce refined microstructure. It is our basic consideration, or is the main concept of our model. Or briefly speaking, that our model emphasizes that this type of initiation characteristic region is formed after the crack initiation. But previous ones, they said it was before. Our model is after the crack initiation, and due to the phenomenon or the mechanism of crack closure and residual stress realization. And then we may have two predictions based on this model. The first is that for positive stress ratios, this type of nanogram layer could be less possible. And the second one is even for negative stress ratio, if the loading cycle is insufficient, this type of morphology will be less possible. And because this type of morphology, this type of feature is in relation to the contact of crack surfaces. And then we perform some further experiments. And this one is just 25 cycles. It's somehow insufficient. And we may see that diffraction is a type of extended diffraction spore, meaning it's a kind of texture phenomenon, not very much refined microstructure. And for this one and this one, there are 0.1 and 0.3 strain ratio. And the diffraction underneath the fracture surface they are all isolated spore, meaning no evidence of microstructure refinement. So this is the verification of the first prediction, and this is the verification of the second prediction. And that's all. Okay. For titanium alloy, we also perform the observation of tests with 0.5 stress ratio, and we observe the fracture the initial region, and we may see a very nice microstructure just underneath the fracture surface without microstructure refinement, and the diffraction pattern isolated spores, coarse grains. And this is also a verification of first prediction. And this is a simulation result given by two German research groups. One is Professor Beck, the other is Professor Zimmer. Their result, or their simulation result, shows that for different stress ratios, here shows the stress ratio of positive ones, like 0.5, without contacting stress at the surfaces. And for negative stress ratios like -1 and -0.8, they have quite a large number or quite a large value of contacting stress. So this is also a result to support this type of process, the contacting between crack surface after crack initiation. And okay, I have shown you some phenomenon and also our model. And here I would like to share with you some of our new results. And this is the first group. And the material is a kind of structural steel. It's a steel very similar to be used in high-strength axles. And this is a fatigue failure just a little bit higher than 10% cycles of loading. And the diffraction underneath the surface is a little bit kind of discontinuous surface. But for the case of 10 to 8 cycles, it's much more loading cycle or fatigue life. And the microstructure refinement is somehow much more evidence, is somehow evident than the previous one. So we said that recognization is for inclusion, and the FGA is a nanograin layer, and this nanograin layer is more developed in 10 to 8 cycles rather than 10 to 7 cycles alone. And also, we observe that crack initiation, or internal crack initiation, may also form grain boundary. But for this type of process, the morphology underneath fracture surface is not very clear evidence of grain refinement. We still have some questions, or we still quite clear about it. We also get some explanations for this, but we still need some further investigation for this phenomenon. And this second set of the newly result, this from titanium alloy. This is an example with crack initiation of surface with rock area, meaning the crack initiation spot is just underneath the specimen surface. And we cut 3 SEM samples, and this is the first one, A1, to show microstructure refinements underneath fracture surface. And this is also an evidence to tell us this type of microstructure refinement process can be found, can be formed under air environments, not just inside, not just a vacuum environment. It's because some results says this type of phenomenon can only be found in vacuum environment, but this is what we obtained recently. And for A2 and also A3 specimens, we may observe that underneath fracture surface layer microstructural refinements. And also for positive, this is the 0 stress ratio, and especially for 0.1 stress ratio, is no evidence of microstructural refinement for titanium alloys. And the third set of example is again a high strength steel, but this time I also mentioned this type of experiment is used for crack growth rate during initiation, and it's due to two-step loading or variable loading. And even for this type of loading, we observe the grain refinement underneath fracture surface. So it's also the same. I think that is okay. Now I will conclude my talk. I think I would show you the 2 schematic of this process. The first one is for high strength steel, initiation from an inclusion, and it's an initiation region of FGA, and we said it's the first transition. And this part is so important that it consumes more than 95% of the total fatigue life. So we should pay more attention on this part. So we have performed quite a number of observations to reveal the nature of this process, of the morphology in this process, and also we try to propose a model to explain the behavior in this region. And this is very similar for titanium alloy, but it's due to the coalescence of the previous visit. And I said we reveal or we know some of such phenomena. I think I put 9 points here. The first, the SN curve is stepwise style, and it's from the quantization is from the interior, and the morphology fisheye containing FGN from origin spots, and the origin is from inclusion and containers from the faces of alpha brain. And FGLI is, we said, is our emphasized point, is quantization characteristic vision. And the related value of theta k is quite stable. And this region can see is more than 95% of total fatigue line. And this region is initiation region is a nanoplane layer. And it is in relation to negative stress ratio cases. But for positive stress ratios, there's no evidence of grain refinement. And we propose or we consider that this region of quark initiation is due to the repeated contact with quark surfaces. And also the quark growth rate is very, very slow. And then we have some challenge or we have some unknown questions. And also I think I put 9 points there. The first is the data pattern between high cycle and VeryHighCycle is quite a large range. It could be 1 and 2 orders of magnitude. So what's the mechanism? And the second point is VeryHighCycle fatigue is kind of internal quark initiated, and if we may identify or we may say there's also a limit for internal quark initiation, internal quark initiation fatigue. We still need more data to identify. And this the third and fourth one, we said, we may ask what is the microscopic mechanism of internal quark initiation, and how about the interactions between dislocations and inhomogeneities, like inclusions grain boundaries. And also, what's the reason for termination of initiation characteristic region? And also, I put the point here, what is the environment for this initiation region formation? We need more data to identify these points, and also we should do some extra or some extra experiments to identify or to reveal the stray field surrounding the quark origin, and also the effect of quark closure and individual stress on initiation. And finally, we should address the process and mechanism of quark closure. In the initiation is a very slow rate. So this is what I like to mention, but we don't know. So we just know little about such questions. It's a new regime. This regime requires more investigations. Okay, I'm very happy to be here, and this picture shows Professor Schematic visited us last year and shared very beautiful work with us in our lab at AMM. And thank you very much.
Thank you, Professor Kong, for this fantastic presentation. high-speed trains, or am I afraid to use them? But anyhow, it is certain that very deep knowledge about these processes is now already in our hands. We are, I guess, all encouraged to deal more with very high cycle fatigue. This is relatively new for us. But anyhow, any questions, please? Milos?
First of all, Professor Kohn, thank you very much for this excellent presentation. It's not a question, just one thinking and about future research. Have you ever performed the analysis of fracture surface by some nano methods, where I think about atomic force microscopy for characterization of the fracture surface in order to reveal the mechanisms, or additional nano indentations, because you mentioned the localized plasticity process. So some other advanced characterization technique, I think, would be very beneficial in this case, in order to reveal the final and mechanism of high cycle fatigue, very high cycle fatigue.
Yes, I agree with you. I think you raised a very, very important comment on this. I think the detailed morphology or detailed microstructure in relation to very high cycle fatigue is necessary for detailed investigation by using some very advanced, facilities like you mentioned, atomic atom or synchrotron sometimes, yeah, to observe something happen inside. So it's a very promising topic and very promising area, I think. Thank you.
You're right.
Yes.
Well, you know my problem with this.
Yes.
And I look at those two SN curves for the initiation in the surface and the initiation interior. And I ask myself, why should the stress to initiate an internal crack be lower than to initiate a surface crack? Everybody knows the surface cracks are much more dangerous, so I can't understand that. And the second thing is that you describe this model of nanograins that could occur for a surface crack too. So why is it this difference? I mean, the model we put forward, there's no reason why it should be confined to an internal crack. And generally, fine grains are good for fatigue. They tend to suppress fatigue. So I don't understand this relationship between the internal and the surface crack, and it seems to be completely the wrong way around on the basis of general theory.
Yes, for the first question, or the first part of the question, is in relation to what you raised during my talk about the surface crack initiation and internal crack initiation. And one of our previous investigation is also that this type of difference is a kind of competition between two mechanisms. And simply, briefly speaking, is that we're in relation with three factors. First is the loading capacity or the loading value. The second is the case, or is the size of the defects. And the third is the strength of the material. Basically, it will be in relation with these three factors. For example, for low strength materials, the very high fatigue behavior is less possible. Okay. And for the second part of the question in relation to the formation of this morphology, we try to identify what caused this type of microstructure, this type of morphology. And finally, we try to propose it is due to the interaction between the crack surfaces. And I also mentioned that before crack initiation, the plastic deformation of plastic behavior ahead of plastic may have some effect, may have some impact on the grain refinement, but it's insufficient to produce refined microstructure like observed on texture surfaces.
Well, can I respond to this? I think mechanistically, everything would favor the surface crack. So because it's got more environment and it's much more powerful than the internal crack. So I don't think it's mechanism. Let me say what I think.
Okay.
I think this is purely a statistical thing. You have a large volume and you have a smaller surface. And the probability of finding a larger defect is greater in the volume than it is at the surface. Even though the surface crack is more dangerous, I think that's probably the primary factor that moves the SN curves down. It's statistical.
Yeah, I think I got a point. For example, the case I saw by Professor Sakai's group is due to or is experience locating bending. It's a kind we may say it's kind of control volume factor. If for the case of local bending, or in comparison with extra loading, the control volume is different. That's one of the reasons to cause the duplex or stepwise curve. And for some other cases with extra loading, the SN curve is almost a trend, only one trend instead of stepwise. So this is, I think, is an important point for categorize or to explain this type of SN behavior.
I think if you argue mechanisms, it's very difficult to argue why the fatigue limit for an internal crack should be lower than the one for a surface.
Yes, that's what I put there. One of the questions, one of the challenge we should further, we need further investigation to, I think we need more data, or we need more investigation to say if it is a fatigue limit at, we may say, 1 billion cycles per day. So someone said yes. We may have two fatigue limits. One is 10 to 7, and the other is something like that. But I don't think we can have a solid answer now.
And just one final point.
Okay.
You have these nanograin structures.
Yes.
I think it would be a good idea to take two materials nominally the same and you could change the stacking energy. Because if you looked at, say, a copper versus a copper alloy, the pure copper would readily form a nanograin structure, but the one with the low stacking energy would not be able to do that. So you could then look and see if there is a real effect of the nanograin structure.
Yeah, this is a type of general question, general behavior of grain refinement. And so far, my results are from two materials, high-strength and also titanium alloy. But if for the material copper, it's quite soft. It is with small value or small value of and tensile strength. But I did see some of the research results for copper with cyclic loading. For such kind of case, a refined microstructure is possible to be produced. Not just on, It's a kind of, I didn't mention this, it's a kind of severe plastic deformation.
Yeah, you're speaking in wearing, so you can change that by changing the spectrum.
Yeah.
The ability to form cells from
Yeah.
is difficult when the spectrum is different.
Yeah, thank you.
Thank you. Vladimir Petrovsky has, I think, some comments.
Just short. I used to manipulate the data, and here is just one specimen. So at certain stress 500, this specimen survived 10 million cycles. Then I increased the stress 525 megapascals, again 10 millions, and then at 600 megapascals specimen broke. So my question is, am I able to say, okay, this specimen, if it was distressed, is it possible that this specimen can sustain such amount of cycles? Just adding one specimen, different stresses.
Can you just a large screen so
Dole desno,
full screen?
malo gore.
Perhaps Professor Rich, remember someone asked me coaching. This is the phenomenon of coaching. Yeah, C-O-A-X-I-N-G. Yeah, someone from Japan, I think, he asked. But at that time, I understand what's coaching, and it's sometimes like to get the material to be reinforced or to be kind of pre-treated, something like that. But I think this type of phenomenon will be in relation to the material propensity. Sometimes I should ask, what is the tensile strength and yield strength of this? Is that right? We should know this.
I mean, no one will ever really explain coaching properly, but I think it seems to me it's associated with visual stresses. You cycle it a low.
Because for some kind of low stress, they may cause some kind of cyclic hardening.
Well,
The other is cyclic softening.
who knows which way, but you're building in residual stresses. And the other thing that can happen is in metallic glasses, you start getting shear bands, and then the practice can go through the shear bands. So it's a prior plasticity effect. It's never really been explained properly.
So again, it is in relation to the yield strength. It is quite obviously below the yield strength.
So it's always local stresses with fatigue, right? It's never global stresses. So even though you're below the yield strength, you're building in back stresses or what have you.
Yeah. So
Here are base metal and different kind of welding procedures.
here, right?
Yes, base metal, three specimens, then laser only weld.
Is tensile strength, right? Tensile strength.
Ultimate.
Ultimate, yeah, tensile.
Ultimate,
Ultimate,
yes.
ultimate.
850.
So your loading rate is obvious, is evidently lower than this value.
Okay, let's go to the other slide.
Yeah, the previous one.
The previous one, yes.
You see, 500. So this is the maximum. I mean, stress ratio is 0.1. Do you think that with Robert? It's amazing. And also, how is the specimen's straight? Is okay. in my opinion, for such a case, there should be no evidence of plastic deformation. And as I know, some investigation or some experiments use this type of specimen again if it doesn't or it didn't fail. And they just take this or took this type of case as a new specimen. They just assume there was not damage even beyond or after 10 to 7 cycles of growth. And what's your specific question? Can you use again?
Is it a stupid idea or is it okay
For what?
to use this, present such?
I think it's clever. It's clever. Because you can save your resources.
Yes, and it's about.
What I said is, for such a case, it seems that no evidence of plastic deformation. I mean, 500 megapascal loading.
But then it should not be key. That's
No.
just not possible. It has to be local deformation. It has to be local.
But we have to check. I mean, if someone said there's a plastic, localized plastic deformation, we have to identify this.
But it has to be. I mean, that was the big mystery of fatigue. That all the failures were below the yield stress threshold. Obviously, it's local stressors, and I think focusing is exactly that.
But it may be for different type of materials, causing. I think.
Well, I mean,
Anyway.
obviously it'll be somewhat different,
Yeah.
but the premier effect has to be local. Back stresses will move dislocation in one direction. It's not difficult. It'll come back again. Motion effects, all these things would play into that. The thing that's of concern, though, some people measure the fatigue limit that way by stepping up.
Yes, this is yeah,
Automatically
yeah,
raises the
yeah,
fatigue
yeah,
limit. So.
yeah. But it's quite it is somehow close to the ear stress value.
But it's never really been satisfactorily explained. No one's really looked at it before.
It's called step loading or something like that. Stepwise. Yeah.
Very commonly used.
Yeah, it's in the standard.
But it elevates the
Yeah,
fatigue.
elevated. Staircase test method for fatigue limit. Yeah.
Okay, I think that we've had enough discussion so far because we can continue right to this door for the small short cocktail and then we can discuss it on the way there and there as well. Thank you once again, Professor Kong.